EECS 281, lecture number 13, midterm exam review, spring 2020. All right. So today we're going to talk about this exam. It's tomorrow. I know you're already excited, getting after that studying. So we'll look at some of the structure of the exam, go over a bit of the practice exam, and then prep up for this one last night. It's hardcore cramming. All right. So this is what it looks like from both sides of the exam. Seldom comforting to students, but it is extremely stressful for us instructors as well. We're going to be offering this exam twice for accommodation of people around the world. The exam starts all in Ann Arbor time at 10:20 in the morning and 10:20 in the evening, right? Both of those are going to run 140 minutes. Gives us a chance to get this thing done. All right, so we've already done a sign up to figure out which one of those you should be on. They are going to be the same exam. It's worth noting that any assistance that you give someone else on the exam only raises their chances to do better on the exam, not so much your own. So let's stick to this honor pledge, do our own good work, and see what we can come up with. All right? We're going to be doing multiple choice questions on Canvas. There'll be some quizzes there. In addition to the Canvas doing the multiple choice questions, we're also going to be delivering the written the wording of the written questions. The written problems, however, will be submitted on Gradescope, much like we do coding assignments in lab. So there will be a separate Canvas quiz, which is the honor pledge. Please fill that out after you complete the exam. If that's not filled out, then we won't be grading your exam. So it's important to get that done. In terms of policies, anything that we have given you throughout the semester is always something that you can use. So if we've given it to you in PDFs or in labs or just by watching office hours or lecture, that's fair game. Anything else is not, right? Normally we offer a cheat sheet, which is going to be one side of an 8.5 by 11 piece of paper, which not as necessary when we've got all of our homes around us, but it's still a great idea. The whole act of getting a focused list of what do I need the most? What do I need the support with? I just want to put this on this one page of paper. This is a great way to study. If you can figure out your study plan for the next, say, 12 hours, that could very well include filling up a piece of paper. You can even divide it into half and say, I'm going to fill this up over the next 6 hours of studying and fill this up over the next 6 hours of studying. Not that you have to study the whole time, but you might study within those times. So making a cheat sheet is a good idea. It combines, especially a handwritten cheat sheet. I know the normal response is to take the stuff that you have and copy and paste it and make a nice document. But the problem with that is copying and pasting doesn't do a whole lot more for your memory. It's just a physical act there that's not really that involved, a finger or two. So when you write by hand, though, it involves a bit more of your memory. You got a motor cortex that gets activated along with your visual cortex, and then you're trying to write things with little loops and circles and lines with your fingers, and it does a different thing inside your mind than just mousing or trackpadding. So that's why we still strongly suggest it, because studies have shown that people who write things down, even if they don't refer to them, which is a great thing. If you study so well and make such a good cheat sheet that by the time the exam comes you don't need it, then you have accomplished your objective. It may seem like a waste, but I promise you it wasn't. Studies have shown that people that write things down recall them better even if they don't look at what they've written down. Studies have shown that people that even pretend to be writing, so people who sit in a meeting and just doodle, draw hearts and flowers and squiggles and your name plus my name and your name plus my name, those kind of things, while completely unrelated to the meeting at hand, has people doing them with a better recall than the people who just sit there and attempt to pay direct attention. So writing something down is a great idea. It helps with your long-term memory. It helps with your short-term memory, so do that. Of course, we do have the engineering honor code. That was why we have the separate Canvas quiz that's just about you signing the pledge. We've had a lot of new things coming at us since we've changed our entire university format. One of the things that we need to do is make sure that we all keep our integrity and we come here and learn the things that we're attempting to learn. So keep that in mind. The multiple choice portion is going to be 24 questions. Each one of those is 2.5 points. Quick mathers will tell me that's 60 points. That's correct. The other stuff is coming, the other 40 points is coming from the written part. We'll talk about that in a minute. But there's going to be 4 to 5 possible answers for each question. It's multiple choice, like I said, A through D or A through E. There isn't any crazy bubbling going on. So each question takes exactly 1 bubble. Not more, not less. Just 1 answer. Make sure you put 1 on for everything. You don't lose points when you get something wrong. You just lose points when it is wrong, right? You don't lose extra points for getting something wrong. So make sure that even if you have a question that you don't understand, proper test taking procedure is to eliminate all possible absolute wrong answers. And then if you've got more than 1 left, take your best guess, right? But if you can find the answer, write it. If you can't find it, use the process of elimination to reduce the ability for you to miss the question, right? Make your highest point total possible by just using good mechanics. So I mentioned this, all the questions are in the Canvas quiz. Multiple choice will be there just like we do in labs. The written questions will be on GradeScoop just like in lab. So make sure that you don't submit the quiz until you're done with both parts, right? That's important because when I say submit the quiz, I mean the Canvas quiz. If you submit the Canvas quiz because the written questions are in the Canvas quiz, you'll be shut out of the Canvas quiz and you won't be able to see the written questions in order to do the GradeScope part. So if you end up running out of time before you get a chance to submit, Canvas will still hold your answers. Don't run out of time. Pay attention. Do this well. But don't add the extra stress of, oh, I know I might mess this up, right? If you answer it, we will eventually get it. But if you want to make this nice, do it well. Finish your stuff. Make sure that everything's done, GradeScope's done, and then submit Canvas. Now, what that doesn't mean is that you don't have to do the Canvas questions first. This is the part where I kind of go off the rails as I talk about how examining should be done. At this point, you're in college. You've been a student for almost 2 decades in many cases, some even longer. But what you need to be understanding is, as a professional student, you are trying to succeed on this exam. This exam is showing what you know. So when it comes time to doing the exam, this is a bit different, but it's still a thing that we can do. One of the first things you should always do in an exam is read every question when possible. Sometimes that's not exactly possible. You get some professional exams that you sit for later in life, and it's a 4-hour or 6-hour exam. It may be a little hard to read the whole exam before you get started. But this is just a normal school exam. You've got 24 questions in the multiple, and then there are 2 to 3 written questions. So you know that going into it. We in 281 really want you to succeed. That's why we're upfront and transparent about the way these exams are going to run as possible. So you know what the structure is going to be. You know what the point distribution is going to be. We put that on every question, tell you exactly how many points each question is worth. So as a professional student, you are trying to maximize points on this exam. Maximize points, that's the name of the game. So the first thing you want to do is start out, read the entire exam. That does a few things for you. The most important of which is it puts your number one ally to work, right? Your number one ally is your subconscious mind. Even when you're not thinking about things directly, your subconscious mind is always at work. And I'm sure you know this, but what you're trying to do is learn how to make that subconscious mind be at work for you. So by reading the entire exam, you know all of the questions that are there, even the ones that are a little bit too hard to figure out while you quickly read through them. I mean, quickly read through them. Don't spend more than 20 seconds or 30 seconds reading a question. You just have to get through it, understand what the heart of it is. Even if you don't understand what the heart of it is, your brain is going to be working on this in the background. So once you've done that, you've read through all the questions, now is when the plan kicks in. What plan, you say? The plan that you made while you're studying. That's what professionals do. You know what they do when they go into a game? They don't just say, hey, what play do you think we should call? What defense should we be running? I don't know. Let's try something. You go into a game with a plan. Gamers, you got to have a plan, right? So you go into this exam with a plan. You know that there's going to be 26, 27 questions you have to answer. You know that you've got 140 minutes. Break that time down and figure out how many minutes per question am I going to get, right? Well, if I say I've got 140 minutes and I want to spend, let's say, a full hour on the written questions. That's 30 minutes for one question, 30 minutes for the other question. That leaves me 80 minutes to go through the other 24 questions, right? Just over 3 minutes per multiple choice question. If you spend about 30 seconds reading all the questions, now you're down to about 2.5 minutes per question. Maybe a half of those, maybe a third of those, maybe 3/4 of those. I don't know. It depends on you. Maybe some portion of those are going to be very easy, or they're going to be something that you can quite directly figure out, right? So then you can say, well, some of those are not going to use the full 2.5 minutes. Some of them are just going to use another minute. And maybe if that's half of them, then I've got an additional 2 minutes that I can spread, additional 2 minutes to spread around. So math is getting a little foggy here because I'm just throwing this off the cuff here. But that's not what you're going to do. As a professional student, you're going to write this stuff down on paper. Figure out exactly what you think is going to be. If I've got a game plan, I'm going to go into it, right? And what do you do at halftime? You make adjustments, right? And you, as the coach and the player and the only person that's going to be driving here, you can call halftime whenever you want. You say, okay, wait, we got to change. This isn't working, right? I thought I was going to spend this much time on the written questions. They're much harder than I thought. They're much easier than I thought. I need to get points somewhere else. I need to go to plan B. That's why you have a plan B. Things change. No plans sort of survive meeting the enemy here. So you come into the exam with a couple of plans. You say, well, I'm going to read everything. And in the case where I think I really can score like 30, 35 points off of these written things because I read them both, they make sense to me. I'm going to dive into them first. Do them first. Then come back and do the written, the multiple choice stuff. Or maybe you get to it and you say, okay, those written questions are a little bit more complex than I expected. Don't dive into them. Put them in the back burner. That's your subconscious mind because you've read it. Put them in the back burner, work your multiple choice questions, and then an hour later come back and deal with those things because they've already been in development. Even though you haven't tried, they have been in development by your subconscious. So get after it that way. The other thing is exams are stressful. Everybody goes into them stressed. That's what our second slide was, is stress. That shows how stress does absolutely nothing for your performance. Does nothing for it. So the more you stress, the less you're going to do well. So don't go in stressed. Go into it knowing I've done all that I can. I'm going to get this done to the best of my ability, and that's what I've got. What happens when you say, okay, well, I'm just going to start out. I need to get these points. That's what I'm thinking. I get these points. I got to start answering questions right away because that's how I get points, with the answers. Well, what happens then is you end up with 25, 26, 27 surprises. New question. Oh, okay, I'm freaking out. New question. Oh, I'm freaking out. New question. Oh, and that happens throughout the entire length of the exam. If you read the exam at the beginning, you get all those surprises knocked out of the way. All of that stress starts tapering off as you're like getting stronger with answering questions. You're like, oh yeah, I already saw that one at the beginning of this exam. I already read it. I didn't quite understand it, but it's not freaking me out. I knew it was coming. I knew it was coming because I have looked forward into this exam. So what I'm saying is, if you're going to be professional at something, and eventually all of us will be professional at something, you have got to be prepared, practice, go into it, setting yourself up to be as successful as possible. And I'd like to tell people, on your written cheat sheet, you should write up your plan A, your plan B, your plan C, whatever plans you want that you want to have in case, well, if the writtens are easy, I'm going to do this. If the writtens are hard, I'm going to do that. If one's easy and one's hard, I'm going to do this one. If it goes really well with the multiple choice, I'm going to do that, right? Set these plans up and draw them out beforehand so that when it comes time, you can say, okay, I'm in the middle of this. Cross those two out. Those are not the plans I'm following. I'm going to use this one, and then I've got another backup plan if things don't go my way, right? So then you can look up and have the minutes on there. Say, well, I'm 30 minutes into the exam. That means I have to have already read this and been through 16 of the multiple choice questions by now. And I can come back to the ones that I don't understand later, but if I'm not on time, it just adds stress to me because I'm thinking I'm going to run out of time. But if I've got a plan and I'm sticking to the plan and I'm right on time, that's one less thing to be stressed about and one more way for you to be successful. So this all comes into, don't submit the quiz until you're done with both parts. But as I said, you don't have to do question number 1 followed by question number 2 all the way up to the end. If you want to do 25, 26, and 27, or 25 and 26, or if you want to do 25 and then come back and do 1 through 12, make a plan so that it's not something you have to think about, because the less non-281 content that you have to think about, the better you're going to do. So you don't have to think about, how am I taking this exam? I planned it, I wrote it down, I'm just sticking with the plan, right? So that's one less thing to think about. All you're thinking about now is answering questions properly, with your subconscious mind also working on the questions. This is how you win. This is how you win. Because practice is what makes it happen. Nobody goes out and plays basketball without practicing first. Musicians don't play concerts without practicing first. This is what we're doing. Be ready for the exam. You have a dress rehearsal in a play. You have a dress rehearsal. Everybody gets their costumes on. They're going to do this just like there was an audience out there. That means I know my times. I know where I'm supposed to be, when I'm supposed to be there, and I'm proving it to myself. This is what you do with your cheat sheet and your exam prep. Set yourself up to be fully successful. All right. The exam has a time limit, right? That's where this thing that comes in here is usually we've got some accommodations for people who have educational accommodations, right? And that's either a 1.5x or 2 times extra time. So that's what's kind of going to be a little bit distracting here, and unfortunately there's not much we can do about that. Canvas only allows us to have one setting, and so we have to have the thing on Canvas set up for a full 2x just in case somebody in that slot needs to have 2x. Even if you don't have, or you're not allowed 2x, if you're allowed a normal 1x, the time limit is still going to say that the entire exam sits for 2x, but you don't have that time. You need to use your time wisely, get in, get out, right? Everybody's going to be in a section, and I don't mean lecture section. There's an exam section. That's how we can subdivide things in Canvas, right? And that will tell you what start time that you requested from the form. You're either on the 10:20 in the morning or you're on the 10:20 in the PM, and if you forget for some reason or didn't submit, you're on the 10:20 in the morning, and you better be there, right? So be aware that it may tell you that you started late because you're not going to get those 3+ hours. It's a display issue. Everybody who has just a normal exam, that means you don't have an SSD form. If you have a normal exam, you've got 140 minutes from start to end, period. Practice exam is posted on Canvas after we finish the last lecture, which is the only lecture today. In the regular semesters, we have multiple lectures, so we don't uncover the final or uncover the practice exam till after the last lecture. That's what it says there, but it'll auto reveal after this lecture around noon o'clock. Lecture slides and recordings, of course, that's a great place to start. We talk a lot. You should hear us. In-class exercises, lab materials, anything that we work in class, we generally work in, a lot of it is C-style. We use arrays, pointers. Right? If you want to practice, take anything that we've written array and pointer style and convert it into vector and iterator style. That shows you know it. Convert it blind. Get the idea. Don't even look at the C-style code. Write it for yourself. That's one way. People always ask me, what can I do to study? Well, here's how you can do it. Convert things. Things that are written recursively, write them iteratively. Things that are written iteratively, see if you can write them recursively. All right? Of course, the projects are going to give you some stuff. We have worked on that. The things that you're going to need most from the projects are just your general syntax and C++ stuff, right? Your basic STL knowledge that you used to be successful in the projects. That's the kind of thing that you're going to be using when you need to write your handwritten problems on the exam. They're not handwritten, I guess they're hand-coded now. That stuff is going to be there. Understanding the complexities of the things that you've done, understanding how priority queues work. That's a big portion of Project 2. How do I use these things? If you've got a study group, that's great as well. I know there's a Discord channel that's been rocking. Talk about things. That's how we get better at this stuff. We're not trying to make this tricky. We're never trying to weed people out of 281. We're just trying to make good students. So if we can get you to be successful, then we're successful. So if that's a study group or whatever, remember in the end you have to do all of this by yourself. Keep it that way, please. But do what you can to be prepared. What we're going to cover is everything up until today's lecture. Well, I guess even today's lecture is going to be on there. No direct questions, though, but you can use this stuff, right? So we'll be especially looking at complexity analysis, including recurrences. And for those of you that have sort of heard this before, this is kind of like the 203 exam, and the final is more like the 280 exam, in the way that we're going to be talking about the more sort of abstract stuff, right? We're going to be talking about complexity issues like that and recurrence and things like that. Later on, we're going to be talking more about concrete algorithms in the final. So we're going to be doing recurrences. So as you look at this, that's kind of one of the things that you can do to approach this, thinking about the way these things come at you. We talked about contiguous versus connected stuff, arrays versus linked structures, stacks and queues, of course, priority queues. We know those. We've used them. We've done them. We've lived them. Boy, I don't know if I can say we loved them, but we loved them. All right, sorting and binary heaps. Make sure you understand how that stuff works. You've done something with your heap-based priority queue. Hopefully that gives you a good, solid feeling for that. The pairing heap, however, will not be on the exam. We've given you more than enough trials and tribulations with the pairing heap just on the project, so fear not. You will not see it again in 281. Elementary, quick, and merge sorts. We have to know those things pretty well. Strings and sequences are not in this format discussed before the midterm, so they will not be on the midterm. If you see something on the exam, this is another aside here that says, if it says heap on the exam, it means a binary heap. So like I said, we're not talking about a pairing heap. In general, anytime you see in literature something that says heap, it means binary heap. The only time it means another heap is when it says another heap. So if you expect it to be about pairing heap, then when you're writing, you write pairing heap. So if you don't see anything other than heap, we're talking about a binary heap. All right, so this is where we jump into the topics, but I'm going to hop over right quick to It was here just a moment ago. Oh, yeah, Chrome crashed. Awesome. All right, so now we get to Duo, YouTube Live. All right. All right, I should just download this beast. All right, so this is what the practice exam would look like if printed on paper. So obviously we're not going to be printing this on paper. We're doing this through Canvas and Gradescope. So what I'm going to do is something I just talked about doing. See that? I'm reading the whole exam from cover to cover. See how good that is? Probably a little fast for the read. But I'm also just not necessarily starting at the beginning. Maybe I'm not starting at the beginning. I don't care about what's going on ESPN either. I'm going to get right to this place where all the points are. Each one of these questions I get right, give me 20 points. All those other questions are just 2.5ers. This is a lot of points here, so I'm going to start making sure I understand how this goes. Here is problem 25 in the old style. Right? In the old style, we were giving you pure STL documentation. We've got to make some adjustments here now that we are at home. So we're still going to have something of this type, but you can see here that I've got a piece of code that I'm going to write. There's things that I can look for on here that I should be using, right? Everything that you find on an exam is still a tool for you to use. Many times, and that's part of one of the reasons why this midterm exam is so hard often, is it's hard to write a question that's clear and direct and doesn't give away too much about what the answer should be. So some of this stuff in the first half, although it's a little bit more abstract, it's actually pretty straightforward. So that's how sometimes the questions end up a little bit more opaque, because it's hard for an exam writer to write a question, be very focused about what's being asked without also giving the answer away. So you can find a lot of information in every question. I mean, the longer the question, as long as the stuff that you're not reading isn't fluff, like so-and-so walked to the store so that they could find, that's the fluff part. But what you should be looking at is the content part of the question. And the more words that are in the content part of the question, the more information that you're being given about the question. So here, as I look at this question, we see that I'm implementing some STL function. So already I can see that I'm working with iterators. I look at the format of this thing. I see I've got forward iterators and output iterators coming in. And then I read more, right? And here, this indented paragraph. Unique copy copies elements from the range. This is telling me what I should be doing. It's got this first to last thing. I've got something that is going to be in every 281 question on an exam about programming. I've got a full complexity specification. This one says complexity is linear, period. All right, that's a good place to start. Then it goes even further and says, for elements in the ranges, exactly the last minus first, it's exactly last minus first applications of operator equals. So it's going to, if you pass in 7 values in a range, it's going to call operator equals 7 times. Exactly. And at most, 7 assignments. Now, what that doesn't say is that I can subtract last from first. Or first from last. I get this right. Right? I can't necessarily subtract first from last because not all iterators work that way. But in terms of the count, that's the number of things that are there. So be aware that we're not trying to be tricky with this documentation. That's the documentation as it's printed on the web. So it doesn't mean that last minus first is a thing you can do. It's saying that last minus first is how we can specify how often these things are going to happen. So that's what's going on in that one. It's telling me exactly that many applications of operator equals. Wait, operator equals is been defined because it's saying it's applying that. So you can assume that regardless of what this is being done on, we've got some iterators that are pointing to something. At the time that I write this function, I don't know what these somethings are going to be. I'm writing a templated function. Whatever somebody sends me into a range, I should be able to handle that. Do I call some functor? No, I don't, because it tells me right here operator equals is going to be applied. So that's great. That's stuff that I can see here. Then I've got some example. This is added here so that you can actually sort of work it out, right? I've got some data that's coming in, room for 6 of those things. I've got some output that's going out, room for 6 of those things. The data are specified as they come in. And then when we call unique copy from data to data plus 6 and get some output, we end up with that in the output. Now, if you've done some work on being ready for this, you understand that output has to have enough room to copy everything over there, because the possibility of everything being unique is a real one. So if I have 6 elements to start with, I may need 6 elements to be done with. So that's why output is of size 6. But unique copy is going to know when it's done how many it actually used. And that is going to be returned in the output iterator, right? Where the output iterator is pointing is the answer to how many things got copied over there. That's what your code has to show, right? So as we get to that, then we have to make sure that that gets responded back, all right? I don't know if I can... I know I can do this. Hold on. I've got to open this in something that I can write on. That's notability, sorry. Send a notability, create a new note. Oh, I just put this in my daughter's folder. That's all right. We'll go find it there. All right, notability. At least I know where to look for it, right? It's right in there. All right, so let's get back to that page. Look at there. I'm going to read the whole exam again. I know you blinked. Got it done, though. All right, so here I am trying to write this, right? Talks about what's going to happen in my discussion there, and then at the very end, there's this section about implementation. It says, use the back of this page as a working area when we're writing. When you're doing this at home, write it down, too. It's a lot of times faster than worrying about getting stuff coded up well. You're still going to type it into Gradescope in the end, but getting it written down quick is still almost always faster there. So get that written down, at least sketch out the directions that you're going there. It might be helpful. Then it says, rewrite it neatly. Not really a point here when we're going to type things into Gradescope. But the limit is going to be 15 lines of code. So we'll talk about what a line of code is later. But 15 lines of code, if you go over that, is going to cost you points. Every line over 15 is a -1 point. So be aware that we're going to tell you what else you can use, right? It says you may not use other STL functions or algorithms, right? Another problem might say you can use anything from the STL, or it say you can use the vector container, or it might say you can't use these functions or whatever. So you're going to be very clearly specified how long you can write it, what you can use, what its time and memory complexity should be. That's all going to be in the specification of the problem. All right, so first thing I want to do here is, as with everything, I want to make sure that I'm not doing unnecessary work, right? While I'm doing this, I'm going to be copying things from this range first to last. If the range is empty, there's no work to be done. In many functions, you can just sort of let the range be your guide. In this case, because we're needing to keep track of this copy situation, so I might have 2 items next to each other that are the same, what I'm going to need then is some other iterator. If we remember about these iterators, we know that if I've got a forward iterator, I can sort of make a copy of that thing, no problem. So in this case, I've got to do an original check to make sure that I don't have an empty range. I can't just let the for loop start, and if the range is empty, nothing happens and be done. So I'm going to start out, figure out if I've got nothing to do, and I can sort of see that by saying if first is equal to last, then I've got nothing to do. That's an empty range. So I've got to return something. What do I return? It says here my return type has to be output iterator. I can't just create one and figure out that's going to be any good for me, but I do know that I was passed one. So great, this looks like if I'm done, I've got nothing to do. Let's just return output iterator, right? Which is result. There we go. Now I've handled my empty case because this is a special function that won't just loop to get it right in the beginning, right? Next thing I need to do is get some sort of starting point established, right? So I need to be able to see if this one is already included, I need to be able to know about the next one, whether or not that one should be included. So I am going to sort of copy the first thing over, because no matter what, the first thing is always going to get copied. Even if the one that's after it is a copy, and I don't want to move that over to the output, I have to at least copy the first one. So from there, I'm just going to use the tools of the idiom, right? This is how STL style, iterator style code looks, right? I'm going to assign a value to this dereferenced output, and afterwards I'm not going to ever write there again. So I'm going to increment that output pointer. But what I put there is what's at my first, right? And I'm never going to copy from first again, so why not just move on? Oh, I did that wrong. Sorry. I'm backing up here. I'm over. Right? I did want that one. I forgot to dereference. My bad. All right. Let's dereference. There we go. I knew that looked funny. I'm looking at too many screens here. There we go. I'm going to write what's in first. I'm still pointing at first. I'm not going to move off of first until I can keep track of it with a separate iterator. All right. So there I've written the first value from the output, from the input into the output. Now I need another iterator so I can sort of inch these two iterators along to see when I get a copy, I can skip it with the front iterator, and I can always refer to the back iterator, say, as long as the front iterator and the back iterator are the same, I need to keep pushing the front iterator forward because I'm only trying to make one of each copy in a sequence to go there. All right. So that means I need another forward iterator. And this was my type as passed in, right? This is the type that has passed in. Forward iterator. And I'm just going to declare one, and I'll call this one prev because this is going to be the previous value. And I'm going to set that equal to what first is equal to right now. And when I'm done, first doesn't need to be there anymore. I've already read from it. I've already copied it. So let's move it. All right, so now in terms of what my input and output look like, if this is my in and this is my out, whatever was here is also there, and my first is here, my pre is there. All right, now as I move forward through this, all I'm trying to do is find something unique under F so that I can write that in there. And for full transparency, that's where R, my result, is. So I've got R sitting there waiting for something unique at F. And by unique, I mean whatever F is pointing at is not the same thing that P is pointing at. Because if F and P are the same thing, I have already written a copy of what P is there. I don't put P to a situation, I don't put P to a location until that value is already copied into the result. So once P is pointing at something, that something is already included in the output. So as long as F is not pointing at something new, there's nothing else to write. So now all I have to do is just keep pushing forward until I hit the end, right? This is where a lot of functions work out. I can just say while first does not equal last, right? And that's another thing that's from sort of the STL style, right? I use these iterators, and because last is always pointing just past good data, last is not pointing at any data item that I want to dereference. I want to keep pushing first until it gets to be last, until it's equal to last, because then it's past all the data. So now I've got a loop here, and what I'm going to do is, as I mentioned, is if first is unique, then I am going to move on, right? So somewhere in there, I'm looking for a test that I can make. And if you remember, from up in the body, it said I was going to apply operator equals equals. Did it say anything about operator not equals being available? It did not. So when I want to say I want to move on because I want to move on until they're not equal, I still have to do that by using equals equals. So I'm going to have to at some point make this comparison. It's going to look something like this, right? That's not it. There we go. There we go. All right. That's something I can do. I know that. But in this case, I do want it negated. So I'm going to put that there, and here's how I worked my way back into this line of code here. So if the thing that first is pointing at is not the same thing that prev is pointing at, then I have something unique and I am ready to copy that. And I copy this exactly the way that I copied it up here. I'm just going to put that exact same line there, right? It's a dereference result for writing. When I get done, increment it. Before I do, though, assign it the value that comes from dereferencing first for reading. All right? So now I've updated it. If first was unique, I'm going to move on. Right? And then, no matter what, I'm going to set prev equal to first plus plus. Right? And so that's a post increment on first. So I'm going to set previous equal to what first is now, and then change first after that. And finally, when I get done, I got just enough room here. I had to put my curly brace on the other page. I'm going to return result. Because we know that as result moves, that's because new data has been written into this. So if my input, for instance, through here was filled with a whole bunch more asterisks, I would copy nothing else there. And I would return this R, and it would be pointing just past good data in my output. And that's exactly what I want. That's how the STL style works. That's what you should understand about this coding question. Make sure that you look at enough STL style, iterator style, range style code to understand how I'm going to be plus-plussing, how I'm going to be dereferencing, and how I want to return the value that lets the caller know how much work was done. All right? So that's that one. We've got another question down here. Let's see what we can figure out from it. I don't think I'm going to do this one, but we'll peek at it just a little bit. Finding max elements. Suppose you're given an array of integers, size n, and a number k. Return the k largest elements. The output does not need to be sorted. You can assume that k is less than n. All right, so that is 3 sentences, but there is a lot of information in there. As you're trying to write this, there's a lot of information in there. First one is just straight up facts. But as we work into returning the k largest elements, we know what kind of information we're looking for. The output does not need to be sorted. That's also important. So you might think, well, I could sort this stuff. You can assume that k is less than n. It's only a portion of this, not the whole thing. As we look into the requirements, your solution must be faster than. Now, that's just a specification right there. We've got a big O of n log n. What does faster than n log n mean? That means it can't be a constant better. Can't say, well, it's a smaller it's only 1 times n log n. No, n log n is still n log n. So one of those things has to be less than n, or you've got to drop down another complexity level to get to something like n or log n, or in the extreme case, can I write a solution that's constant time? Probably not. But something that is better on our list of complexities, right? And here it is. Look at that. We're looking at this from the study slides. Here's n log n. It says it has to be faster than that. So it has to be a better version of this by having something smaller than n in one of those positions, or one of these 3 things, right? Has to be 1, big O of 1, big O of log n, or big O of n. So that's what we're getting out of this, and that's what you should be. Okay. Today is a good day. It's going to be a good day. All right, there we go. Took a minute there. We got it. Okay, solution must be faster than. So that's what you've got out of that. You can use up to a linear amount of auxiliary space. Means, sounds like I can make a full copy of this thing if I want. I can have a separate value for each one of these things. Do something here. All right. I've got a linear amount of additional space. And then I've got the implementation area. Limit 15 lines of code, points lost for more. You can use anything from C, C++, or STL. Anything that you wish. There you go. There's your requirements. 15 lines. It's wide open in STL, C++, and the like. But make sure it happens. All right? So if we got time, we'll hop back to maybe check this problem out. But that's what you're looking for. We're going to be looking at one question in the written section that's more straightforward STL. And the second one is just going to be something that's a problem solving using possibly some of the containers or algorithms that we've looked at in this first half. So that's what you're looking at out of these 2 big point problems. All right, back to the other stuff in the slides. So here's complexity analysis. We've already had a chance to mark this bad boy up. But we saw this slide earlier in the semester. This is just something that should be well fixed in your mind by now. You should be able to recite these in increasing order and decreasing order. I should be able to give you any 2 of them, and you can tell me which one is larger and which one is smaller. This is the basics here. Make sure you've got that stuff down. As we look at a couple of pieces of code, we talked about how do we figure out the complexity. We look at the stuff that doesn't matter, the stuff that's the same, no matter what n is. Is it a multiplication? Is it an addition? Is it a comparison? The things that don't change with respect to the amount of input, those things we just sort of looked right past them, right? We realize that any one line that hasn't called out to another function, if it's just got a constant amount of work in it, it's just a thing that's unimportant. What's important about driving the complexity of our functions is going to be any sort of recursion, because we got repetition there, or iteration, more repetition. So you're looking for while loops, for loops, calls to ourselves. So as I look at these 2 pieces of code here, I can see that the first one in the background there, the entire body of the function is all about the while loop. So there we start out with the while loop itself. Further investigation tells me what? I'm going to stay in this while loop as long as high is greater than or equal to low. So that's where I get my n from. Then I just need to see how through every loop does this change. Am I plus-plussing? Am I minus-minusing? Am I multiplying or dividing by 2? That's what you should be looking at as you're trying to track down how often or how does a loop modify itself as it works through there. So as long as high stays greater than low, that's great. I look inside it and I see, well, I've also got this new thing mid, and I look through the end of the line. I see there's nothing but a bunch of assignments and math operations. So this is a constant amount of work in line 3. Great. We can ignore that. We just know that we've got this new value mid that we might be using. Then as I look in here, I say every time through this, I'm either going to be adjusting one of my range components, the low or the high, with relationship to the mid. So here, low gets pushed to mid +1. There, high gets pushed to mid -1. All right. So I know that every time through here, mid is going to be important. If I go back and look more closely at this, I see that mid is what it sounds like. It's the thing in the middle. We have taken the range and divided it in two. So I either find it and return the value that I was looking for, or I cut out half the data. Already, you see division modifying how much I'm going to do my work. I'm probably looking at something logarithmic. If I see multiplication modifying it, multiplying sort of like my iterator jump or whatever, is there multiplication or division involved in how often I'm going to do my loop? Chances are you're talking about something that is recursive, right? I'm sorry, not recursive, logarithmic. All right. Second piece of code. What do I have there? For loop starts it all. All right. It looks like we have reconnected. Sorry here. We have some, I think that was a power problem. Sorry. All right, we're on the adapter here. All right. Sorry about that. I don't know. I think we had a machine went to sleep on me here. One of the fleet. I believe we're back in action, though. Okay. So I left off talking about this front piece of code. The for loop inside a for loop. I multiply those complexities and I've got it. So I can see there's an n loop inside an n loop. This is just n squared. Everything that's not the for loop in lines 10 through 19 is some constant amount of work. All right, so I see a log n, not surprising, it was binary search. And then whatever this 2D thing is doing here, I can see that's an n squared. That's the kind of thing that's going to be at... See my face, no slides. All right. Let's see if we can't return the slides. Bring them back. And there we are. All right. It's good. All right. So, we pulled this one off while slides died. Hey. Big O n squared. Big O log n. That's our two pieces of code. So this is what I was saying is the fundamentals. You're going to have to at least be able to manage something like this. You see a piece of code, chances are it's not going to be this obvious or quite this simple. But that's what you need to do. You need to look at the loops, figure out what's constant. These are pretty straightforward. They don't have any calls out. So another way to make this a little bit more complex is say, well, what if I make calls out to another function? Sometimes I can show you that other function. Other times I might just say we're making a call out to another function that is of linear, or another function that's a log n function. How many times do I call out to it? How does that modify what this function is doing? So these are the pretty basic examples. As you're studying, try to think of more complicated examples. Swap a few on the Discord. Say, hey, what do you think the big O of this thing is? And drop some crazy bunch of loops out there and see who can come up with the right answer. Talk about it. Understand it. All right, how about this one? Another complexity question. But looking closely, you can see right away that it's merge sort. So we know the answer for one. But the other thing that's important is you see that merge sort calls merge sort. So I've got some recursion going on here. So I'm not going to be able to pull this off just by saying, well, merge sort is n log n. I'm just calling it there. What I want to do, though, is be able to do the analysis here, right? So write the recurrence relation. So how do you write a recurrence relation? You look at the objects, the lines that make up the code, and you think when I come in, I'm trying to figure out when n is my input, how much time does it take to do n, right? And with recursion, unless it's going to be unbounded, the next call always has to have some smaller input, some t of n minus 1, because that's smaller than n. T of n over 2, that's smaller than n. Even 3 times t of n over 4, that's a smaller version of what's going in because t is being called with something smaller. So, and when you're trying to identify, when you're looking at a piece of code, is how does one call that starts out at t of n, what does that lead to? Is that going to lead to another call that's t of n over 2 or t of n minus 1? In this case, it looks like there's 2 calls. T of n gets called, and it makes 2 calls. But each one of those looks like it's half the information. So I'm looking at a 2 times t of n over 2. Right? So that's what I get out of these 2 lines right here. This is a t of n over 2. This is a t of n over 2. What about the other things that I had in there? Constant work, constant work, constant work. What do we know about merge? Merge takes all of those elements and puts them into an output container. Everything from left to mid and everything from mid to right. So this is going to be linear in all of n. So you can see that I'm going to put some more work in there. And so that's how I come up with this recurrence relation right here. Here's the 2 recursive calls, and there's the merge. That's the complexity of this function. If I've got no data here, obviously I've got no work to do. There's my base case. This is a recursive function. I can't have a recursive function without a base case. I can't have a recurrence relation without a base case. It's recursive as well. So without a base case, I don't have a recurrence relation. All right. I can solve this, of course, with the master theorem. That sounds like a good way to do things. I do have the proper structure. I had 2 times t of n over 2 plus n. That's what my f of n is looking like, something that's a linear function. So if I plug those things in, then I end up with an a of 2, a b of 2, and c being the degree of this polynomial was just 1. So c is 1. So I end up with 2, and comparing that to 2 to the 1. A compared to b to the c. They're equal. I'm going to end up with this version right here. N to the c, that's 1. You get it, right? N log n. We knew merge sort was n log n, but that's just me showing you an example of working through the recurrence relation, working through the application of the master theorem to get to the final answer. As we talk about containers, what's the best container? Get that question all the time. Should I use this? Should I use that? I actually kind of don't like that question a lot because we talked about it so often in class. We give you so many things to do, and what you should be doing is asking that of yourself. Which one is the best? What am I doing the most? I can go look at the actual complexity of these things, and I should be able to answer these questions. It's not like I have to go figure out what the complexity of vector pushback is. If I go look at the documentations, it tells me. So if you've got the information in front of you, put it to the test. All right, so that's kind of what these are. These questions are really bad exam questions, but they're really great study questions. A good study question has good material in it, and then it's sometimes right and sometimes wrong. Why? Because it depends. It depends on what the focus of the actual question is going to be. So this is a general purpose question about containers. And when you get another question, as I mentioned earlier, there's going to be some additional wording in there. Some way the question asker is trying to focus your attention somewhere. And so that's the part that's going to bring the what it depends on to your answer. So these are good ambiguous test preparation questions. They don't make good test questions though. So this one, I'm looking at some containers and I've got 3 options. What is the best container if it will be used primarily to locate objects within it using a binary search? What is the best container if new objects will often be added immediately before specific existing objects? So you've got a specific object that you're putting it in front of. What is the best container if you must store a small number of very large objects? Memory is scarce, and the most important consideration is to store as many of these objects as possible. Now, I've got 3 options here: a singly linked, doubly linked list, or a vector. So in practicing, you should be figuring out how to apply which one of these and also why. So the first one, if I'm doing binary search, I know that I like to make these large jumps. I know I've got 50 items. I want to look at the 25th item in constant time. Instantly rules out singly linked, doubly linked list. So I'm going for vector here. That's good. Second one, what's the best container if new objects will often be added immediately before specific existing objects? So I've got the object. That's what it's saying here. You've got the object, then how do I pick which one that's going to be? Well, if I've got a specific object, I want to insert something before it, I know that those insertions are going to be linear with the vector, because I have to move everything. And when I'm inserting into a linked list, it's always constant time. So there's a break right there. Vector's out. I still have to decide between singly linked or doubly linked list. And it sounds like they're giving me a pointer to the object that I'm inserting in front of. So if I want to find the previous to this object, I need a previous pointer to get there in constant time. Or I have to next my way there in a singly linked list, making it linear. So this one sort of rules out the singly linked list, and we're going to put that right there as the doubly linked list. All right, last one is another example of what I was talking about. Just look at it physically. 2 lines, first dot, 2 lines, second dot, 4 lines, third dot. So there's a lot of additional information in there. The question asker is certainly trying to focus you towards something and away from other things while not trying to give away everything. What is additional, right? You can see the first questions kind of stop after one sentence, right? So if I read this last one, what is the best container if you must store a small number of very large objects? Boom. That was enough for the first 2 questions. That's not enough for this next question. So what makes the depends go away is this next sentence. Memory is scarce, and the most important consideration is to store as many of these objects as possible in the available space. Memory is... Oh, bad thumb. Memory is scarce. All right. So I don't want to use any more pointers than I need to. Right? So this one is trying to sort of shoo me away from a doubly linked list. This one is trying to move me towards a singly linked list. That's the way I feel about it. Right? So, and you can also say, you can sort of do some deduction here. It said I had 3 choices. I've already used 2 of them. Sometimes that's good enough to be like, okay, this rules out and I'm going to pick the third one no matter what. Sometimes it's not quite that clear, but both of those 2 things should have been pointing me towards singly linked list. In the end, I know that if I've just got 1 pointer overhead, I've got these very large objects, right? So that's what's important about this. You say, well, if I wanted to put as absolutely many in there as possible, then maybe just putting it in a vector, not having any pointers is there, because, you know, that's wasting memory. But if I've got a small number of very large objects, that means I have a small number of pointers. It also means that the very large objects vastly overshadow the overhead of the pointer, so I don't really worry about, you know, if I've got an object that's, you know, 40 megs that I'm trying to put into memory, I'm not really going to be concerned about the 8 bytes of the pointer that gets me to it, right? So, as well, I can't say, well, if I save that 8 bytes, that might let me get another 40 megabyte object in there. No, you're not going to get another 40 megabyte object into those 8 bytes that you've saved by saying, well, I'm going to not even going to use 1 pointer for it. So, those are the things that you look at in the depends of that long second sentence there. It's all sort of those things bouncing around there. And you see here, that's what our answer sheet has. Vector, doubly linked list, and singly linked list. All right, let's try it again. Same options, singly linked, doubly linked, and a vector. 3 new questions. Now we're talking about worst options. What is the worst container if you must store a large number of 1 byte items and memory is the scarcest resource? All right, you should have some ideas there. 1 bytes, I want to have a large number of them. So anytime I've got an extra pointer, that's 8 things that I can't store, right? If I got 2 pointers, as in doubly linked list, that's 16 objects I can't store. And if I've got them in a linked list, I've got 16 bytes worth of pointer for every 1 byte of data. And now I'm looking like only 1/17 of my total memory is going to be usable. So that's not great. So in terms of the worst here, I'm going to go right to doubly linked list. Vector probably being the best here because it's the most condensed, right? Once you get up above getting past that 24 byte overhead of the pointers on the vector, it's all just pure data. That's good. Second question, what is the worst container if you will frequently insert new items anywhere within the structure? Right? So anywhere within the structure means I could be pushing things around. I don't probably want to do insertions into a vector. It's probably going to be the worst.
Okay, turning you off. Okay, everyone, I think I'm in charge here now. So you'll be a little bit behind me. Marcus, I think you're actually... Okay, turning you off. Okay, everyone, I think I'm in charge here now. Okay, so I've got picked up where we left off, or at least I should have. Okay, so we're on this slide. I don't know where we left off on this slide, so we'll go through this slide. So we're talking about the best container if we want to locate objects using binary search. So we've got our choices. So singly linked list, doubly linked list, not going to work because we don't have operator square brackets with O of 1. So it's got to be vector. If we had some other choices, what if we had also DAC and array? Well, either of those would work for binary search because all three of these have O of 1 operator square brackets. So all three of those would work. And then what's the best container if we're going to add them immediately before existing objects? If we're going to add them before an object, we would need to know who points to this object. So we would need, oh, you're in the worst case. Okay, sorry about that. All right, over to here, worst cases. Sorry, like I said, and once I took over the video, I lost track of his screen of showing me the preview of where he was. Okay, so the worst container if you have to store a large number of 1-byte items and memory is scarce. Well then, if we go with linked lists, granted there's only one node per item, but we've got a lot of bytes of pointers. If we've got 1-byte items, in a singly linked list, we've got 8 bytes of pointers, and in a doubly linked list, we've got 16 bytes of pointers in every node. So then, doubly linked would be the absolute worst. The singly linked would be bad. Vector would be our best one. Vector would never be more than twice as big if it grows by doubling. And if we set the size to begin with, it'll be exactly the right size. Now, granted, the vector has a little bit of overhead because a vector basically has the size, which is 8 bytes. It's got the capacity, which is 8 bytes. And it's got a pointer to the heap, which is 8 bytes. But this is for the whole vector object, not per node. All right, now what is the worst container if we're going to frequently insert items anywhere within the structure? Well, if we're going to insert them anywhere, what does anywhere mean? Anywhere to me means, like, what if I had an iterator? If I had an iterator, putting something into a doubly linked list is pretty easy. Putting things into a vector would be hard because if it's anywhere near the beginning, then we've got to move everything over to make room. So the vector is going to be bad if we're going to insert items anywhere, beginning, middle, end. Vector's great at the end, bad at the middle, terrible at the beginning. What if we were going to frequently insert items at the beginning? Well, that's definitely vector. And we looked at when we looked through the STL slides, we saw how when we insert things at the beginning of a vector, it's the absolute worst data structure for that. Okay, stacks and queues. So we've got a question here, which will give me a second to catch up and catch my breath here from taking over. It says we want to implement a queue using 2 stacks. And we've been given what we have below. We've got, so I'm going to make my queue class Inside of it, it has a stack S1 and S2, and we're going to talk about this a bit, and then I'll give you a minute to work on some code. So push has already been written for us. We need to write pop. Now let's look at an example before we start digging into code and writing code. So if I've got internally, I've got S1 and S2. Okay, so I do the operations, I say like push 1. Okay, so 1 goes on to stack 1. I say push 2, right? 2 goes onto there. And I push 3. 3 goes onto here. And then we say, hey, we'd like to do a pop. Now, if we learn how to do pop, we can write the front also. Normally, we would look at the front before we pop it, but let's just write one of these. If I did push, 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 pop, I have to get rid of, since we're supposed to be writing a Q, I've got to get rid of that 3. So to get rid of the 3, the only place I can get rid of anything is from the top of the stack. So that's where S2 comes in. Let's move 3 over to S2. Let's move 2 over to S2. And now I'm going to keep going. I'm going to move 1 over to S2. And I'm still in the middle of pop. Now I can finish my pop by getting rid of this. I pop the top of S2. Now, before you start coding this, what I want to look at is, do we have to move those things back over to S1, or could we leave them here? If someone was to say, do another pop, it would be better if we left them here, because another pop, we can just get rid of that too. Well, then if we do leave it there, what happens if someone does a push of 4? Push is already written. It says 4 goes at the top of the stack. And I'll draw it there, even though it's sort of at where the 1 used to be. But just so I don't make it too confusing, we put a 4 on the top of S1. If someone says push 5, well, we push the way the push is written. It says put a 5 there. If someone says do a pop, well, we just get rid of the 3 that's in S2. Okay, so take a minute or two, write some code down, and we'll come back and talk about this. Okay, so we've got our code for push already written. We need to implement pop. We saw that we need to move something over to S2 to pop it, but if it's already in S2, then we can leave it there. And we don't need to move everything back to S1. We could, but we don't necessarily have to. Okay, so let's look at the code on the next slide here. So it says, if S2 is empty, we have to move things over. So we say, while S1 is not empty, move the top of S1 over to S2, and then pop the top off of S1. And it was easy to write this to move everything over there. It would have been a little bit more complicated if I wanted to move all but one of them. The code would get a little bit more complicated because now I've got this if. If S2 is empty, move everything over to S2, and then I always pop the top of S2. If I'm at the point where I did the 1, 2, 3, and someone says pop, so this is S1, S2, I move the 3 over, I move the 2 over, I move the 1 over, and then we pop this one. Now, if someone does a push, we put a 4 here. If someone says pop, we say, is S2 empty? No, S2 is not empty, so we just pop the top off of S2. So this will work just fine. It's a little bit of extra work to move everything over before we get rid of the top of S2, but it makes the code simpler. It's certainly less work than moving all but one of them over, popping it from S1, and then moving all the others back to S1. It's certainly less work than that, and it gives us a really simple code that if we have to move things over, we do, and then whether or not we move things over, we pop the top of S2. If we wanted to write the front member function, so if we had to write front, it would look basically the same, except here in line 18, we would say return S2.top. So S2.top is the front of my queue. Okay, some questions on sorting. So it says here, unless otherwise stated, use the best, meaning the most adaptive version of the sort that we've developed. So it asks for which sort is best in each of these circumstances. And then the other question is, it says you're using a quicksort on a very large input and it's taking longer than normal, meaning longer than you would expect for quicksort to take. Why? Why is that happening? Okay, so take a few seconds, think about these, and then we'll come back and talk about them. And some of these are a little bit vague. I wouldn't consider this a good exam question because it's vague on what exactly we mean by medium and very small, etc. But we'll look at getting our best answer out of this. Okay, so come back to here. I noticed there's a typo in the later slides. We'll get to that in a minute. Okay, so we're talking about this one. So we want to know what to do with an array that's almost sorted. Well, if it's almost sorted, it partly depends on what almost sorted means, but we saw that insertion sort does really well if we've added an item to the end. That's almost sorted. If items are very close to where they should be, even if there's a lot of them, bubble sort and insertion sort don't both do really well. If there's a few elements that are very far out of place, like adding to the end of a sorted region, insertion sort works great. Bubble sort can work great depending on which direction we bubble. If the direction of the bubbling matches the direction that the items are very far out of place, then bubble sort works well there also. For very small, what do we mean by very small? Well, we talked about this when we did the elementary sorts. The insertion sort is the best sort there is when we're talking about around 16 items. Nothing beats insertion sort. Even our more complex sorts that have a better worst case of n log n still can't beat insertion sort on small arrays. Let's come back to medium because that's kind of vague. Let's go to very large, tape drive, meaning it doesn't fit in main memory. Yes, tape drive is outdated, but we've got something that's bigger than our main memory. If it's bigger than our main memory and we have to sort it on disk, that's what merge sort is intended for. That's what it was developed for. Okay, so then let's go upwards from there. So for a large array that's about as big as main memory, if it's that big, we don't want to use one of the elementary sorts. We could use merge sort, but wait a minute. If I use merge sort, it's fast for that large amount of objects, but because merge sort needs an extra area of size n in which to do the merging, then we can't use merge sort because we don't have the memory for the copy. What about heap sort? Heap sort is guaranteed to be n log n. It needs O of 1 extra memory. It does it in place. Heap sort would be fine. Quick sort has now it's showing that I'm buffering, but it seems like I'm not. Okay, my preview is messed up, but I think I'm doing fine. So for the large one that's about as big as main memory, we don't want to use merge sort. We don't have room to merge in. We could use heap sort, would be fine. We could use quick sort. Now remember, we've got extra room for the quick sort recursive calls of log n, but even a billion items, we only need room for 30 items on the call stack. So it should be fine to use quick sort there. And the reason we don't want to use selection sort, Samaya, is selection sort is n squared. And I'd like to avoid n squared if it's a really, really large number of elements. Okay, so then for medium then is between the very small and between the large. So something that's in that range, the general go-to is quick sort. Heap sort would be fine also. Quick sort tends to be a little bit faster on average because it makes better use of the cache. Okay, so there's our answers. We'll get that slide in there so it's in the video visual portion also. Oh, whoops, forgot. Quick preview. Sorry about that. I forgot there's another question here. So the other question here was, quick sort's taking too long, longer than we expect it should take for an n log n sort. So for an n log n sort, to be taking too long, remember n log n is the average case of quick sort. It's not the worst case. If it's taking too long, it means quick sort has degenerated into its worst case of n squared, and it keeps making bad pivot choices over and over. Bad pivot choice followed by bad pivot choice followed by bad pivot choice. Okay, binary heap question. Good thing for a quick practice here. It says draw the underlying array for this, push the value so 47, meaning we have to get it into the underlying array and we have to then fix up to get it back to where it should be and show what it looks like afterward. Now drawing the underlying array or vector, not too bad. So when we push 47, we want to add it to the back of the array or the vector. So let's just pretend that the vector grows, it makes room for 47 here, and maybe some other stuff because it's a vector, it grows by doubling. So we've got room for 47 now. In our binary tree representation, it would look like this. 47 would be to the left of 7. Now, we want to move things upward because we've increased someone's priority. How did we increase? We added something. But imagine that what used to be at 47 had an infinitely low priority. That's why it was at the end, because it had a lower priority than anything else, and its priority went from infinitely low to 47. So we've got to fix upward, fixing the priorities. And it's assuming here, in the exam we would be careful to say, but if we are careless, if we don't say otherwise, well, obviously, if this thing is correct, this is a max heap. And like I said, on the exam, we try to be very careful about this and say max heap or min heap. If we don't say otherwise and we don't make it clear, assume it's a max heap. Okay, so we've got a max heap here. So we've got to fix up. So we checked 47 versus its parent. It's a higher priority than its parent, so we swap. So 47 and 7 swap. Whoops, I just swapped with itself. Let's try that again. Okay, so we swap the 7 and 47. 7 moves down, 47 moves up. And in the array representation, 47 and 7 swap. Really, what's happening is the array is being manipulated, and our logical, our mental view of the tree is also changes to reflect that. Okay, so let's look at the array. We've got a 47 at index 5. Its parent must be at index 5 divided by 2. Integer division says 2. We compare 47 with its parent. It has a higher priority than its parent, so we swap. And over in the tree representation, we swap them. And then we compare index 2 to its parent at index 1. It's not a higher priority than its parent, so we have finished our fix up operation. 47 has moved back to where it should be, and the heap property is restored. So we end up with 81, 47, 14, the 1 and 5 stay the same. 9 and its children, 2 and 4, stay the same. 47 has a right child, 18. 18 has left child, 7. Remember our sort of curved arrow there to make room for that node. So this is what our tree looks like when we're done, and our array has been filled in and overwritten with correct values. Now here's a table of the different implementations of the priority queue, and we want to know what the complexity is. And notice that we left pairing heap out of this. This is exam review. On the exam, we don't expect you to answer any questions about pairing heap. We've done enough of that with the project. Okay, so for this one, let's go through one container at a time and stay with one container. So when we look at the unordered array, to create a range, meaning to create from a range-based constructor, it would be the time to copy everything, big theta of n. So it'd be big theta of n, because we have to copy everything. Let's say we wanted to create an empty one. Well, that should be pretty easy. This should be O of 1 for all of these. To create an empty one is easy. Okay, I said we were going to stick with one container, but the create empty was too easy to pass up. Okay, so let's look at pushing. So in the unordered, when we push, we just add it to the back of the underlying vector. And that takes big theta of 1 amortized, because it has to be added to the back of the vector. Now when we ask for the top of the unordered PQ, I have no idea where it is. I've got to go searching through every item in there, and that's, whoops, one typo on that one. This one really should say big, well, we usually say big O of 1 with amortized. Okay, so for the top, it's always going to be big theta of n. We've got to search through everything before I know where the highest priority value is. Now, when we get to pop, the complexity here is going to depend upon whether we're talking about the unordered PQ or unordered fast PQ. In the unordered PQ, we have to do our big theta search all over again. In the unordered fast PQ, the reason it's fast is that it assumes that you're going to have a certain type of behavior. It assumes that most of the time you're going to look at the top before you pop it. You're not going to just push a bunch of things and pop them out without ever looking at them. You're going to tend to push some things, look at the top, pop it, and whether you push more things or not, you're generally going to look at the top before you pop. And so what the fast PQ does is it says, if you do a top and you have to do that linear search to find the most extreme element, remember its index. When you get to pop, if you know the index, just get rid of it. And we did it in big theta of 1 time. Now wait a minute, what if it's in the middle of the vector? If you look at unordered fast PQ, what it does is it says, oh, let's swap that item that you want to get rid of. Actually, not even swap. Let's overwrite the item you want to get rid of with what's ever at the back of the vector, and then pop back. It is unordered. In fact, it demonstrates why it's unordered. I had something like 2, 3, 4, 1, and another 2 over here. And let's assume it's a max heap. So I said, oh, let's make this a 2.5 just so it's easy to see. So I say, get rid of the most extreme element. I say, show me the most extreme element. Top looks through everything, and top says, oh, this is the most extreme. This is where it is, and I remember where it is. When I do a pop, it says, well, I know where the most extreme element is. Let's replace it with 2.5, and then let's pop back. Now remember what we said about unordered containers. Unordered means one operation might cause other things to change their relative order, things that aren't involved in the insertion or deletion. So because 1 used to come before 2.5, and neither 1 nor 2.5 was deleted, after the deletion, they have a different relationship. Now 2.5 comes before 1. This is really an unordered container because I didn't delete 1 or 2.5, but they changed their relative positions when I popped something else. Okay, let's move over to the sorted container. When we do the sorted container, we've got to push at the correct position. We've got to find out where it should be and make room for it. So this is O of n because even though I can find where it should be in log time, if it's near the end or even near the, if it's near the end, it'll be fast. But if it's near the middle or the beginning, it's going to take O of n time to move elements over to make room in the vector for a new element. When I ask you where the top is, that's easy. It's O of 1. It's at the back. We put the most extreme element at the back. Top is fast and pop is fast. We just say data pop back. All right, what about the binary? Well, oh, I forgot the sorted create a range. Forgot that one. So when we create a sorted range, it takes us n time in order to get things in, but it takes n log n time in order to sort the whole thing. So it takes O of n time to copy, but then n log n time to sort that copied data. All right, what about the binary heap now? When we do the create range, we have to copy everything over. That takes O of n. And then if we do the bottom up fix down, if we do bottom up fix down, this takes O of n time to do the bottom up fix down, to turn an known ordering of stuff into a valid binary heap takes O of n time, and we do that, proceed from bottom to top, meaning highest index to lowest index, call fix down on each element. If we call fix down on the leaves, fix down does nothing. So we really would want to go from the highest index that has children all the way to the smallest index and call fix down on each of those. So that takes O of n time. Push, we just did a minute ago. We added it to the back of the vector, which is O of 1, but then we had to do a fix up. The fix up can't go higher than the top of the tree, which is O of log n. All right, what about top? Top, we know where it is. It's at index 1 or index 0, depending on how we implemented it. That's O of 1, to look at the top. And then pop consists of replacing an element with what's at the back. Pop back, fix down, is O of log n. Because the overwrite with the last element is O of 1, pop back is O of 1, fix down only has to go as the height of the tree. The height of the tree is guaranteed to be log n because of the complete property. Okay, so there's all of those. Okay, now there's a few slides here just about answering coding questions. This one I just noticed. I updated these for the electronic format, but I forgot to update something on this slide. Write it. So if you decide you need a helper, write it above. If you write it above the given function, it'll compile. If you write it below the given function, you would have to put a prototype above the given function. Easier just to put your helper function above it. I don't think in this exam, I don't think you really need helper functions. I would tend to not write it this way. There's a function that you need for one of the problems, and we told you that it exists and you can use it. But we didn't show, you don't have to actually implement it. If you decide you need something like a structure, you can write it inside of a function, you can write it above again. Just make it legible, and preferably we'd like it to compile. Now this is a good thing about Gradescope to answer is, what if your code doesn't compile? Then we'll do it like we would do it in a normal semester. We will grade you entirely by hand. If your code passes all of the test cases, we will still look at it, mostly to make sure that you didn't violate any of the constraints. So if you don't compile, we are not going to hugely penalize you for not compiling. We are just going to take the time, like we would in a normal semester, to hand grade it. Okay, so on lines of code, how many lines of code is this? It's 2 lines of code. You can write it this way if you want to, just to save a little bit of space, but we will count it that way. Now, with the handwritten exams on paper in person, this version is a little bit nicer just because it saves you some vertical space on the page. Since you're going to be typing it, I would just go straight to this version, since you're going to be able to type it. How many lines of code is this? It's 3 lines of code. We never count curly brace lines against your total. What about this one? This one counts as 4 lines of code. The else counts as a line of code. Now, if you added curly braces to this, it's still 4 lines of code because the curly braces don't count as lines of code. Curly braces delimit code. They are not code themselves. Could you write this one with the ternary operator? Sure. If you want to, you can. Our coding problems on the exams don't tend to need it, but if it would work, you can do it, but our line count would be based on not using it because we don't expect you to use it. If something like that is true, we would write it without it. We would base the line count on our version without it. Comments, no, comment is not code. Comments is talking about code. So if you want to add comments to make it clearer what you're doing, that's fine. It's up to you. I would tend to, on the exam, not spend too much time on the comments. Now, how do we get our line counts? So we write a straightforward solution. Like I said, we don't pull out the ternary operator. We write a straightforward solution, and then we do kind of what the autograder does. We'll add about 50% or so to it. So if we give you an assignment that says, like, let's say 20 lines of code, it means we did it in about 12, maybe 13. So we give you about a 50% buffer on your line count above ours. Every coding question will tell you what you can use. So in the coding questions, if you're allowed to use stuff from the STL, we're going to put a bunch of include statements in there. You can add to it if you want to, but you don't have to. Just use whatever you are allowed to use for that particular question. Okay, now that's the end of the slideshow. There's one thing that I wanted to talk about a bit, which is Professor Darden never got back to the last written question. And it's going to take me just a second to grab that. Okay, exam 1. Let's go to the practice exam, not the real one. And we've got our practice exam. Where's our midterm combined? We got our answers, etc. Let's just look at the answers one, because this is visible now. No, I don't want a new version. That's fine. Okay, oh, whoops. Oh, now I've got to scroll through. Okay, so for this problem, the last one, there's two different solutions here. So there's two different solutions here. It outlines them and what their complexity is and explains it. There's two different approaches, and it talks about in the comments creating a max PQ or creating a min PQ. If you haven't done this yet, don't look too closely at the slides. Go try it without looking at the answers. But when you're done, go back and look at the comments for it. Okay, so we're all done for today. We're going to get the exam. I would have been editing it now if I hadn't had to take over the video. So the exam is going to be made public soon. You'll be able to see your time slot on the Canvas quiz. It'll show you what time you start and end. Submits to Gradescope is unlimited because you're not getting feedback. So if you decide to upload a new version, just go ahead. It'll accept it. You're not going to get any test case feedback from Gradescope. Unlike the labs, you don't get graded feedback during it. But the Gradescope, you can submit as many times as you want. For the Canvas quiz, you can only submit once. And like we said near the beginning, don't hit that submit button. Where's our notes on that? Yeah, don't hit the submit button until you're done with both parts, because the Canvas quiz is where you read the question. Gradescope doesn't have anything about the question. Gradescope just says, hey, here's problem 25, submit me an answer. Because Gradescope, we can't assign a time slot to Gradescope. So Gradescope will be open, but we're going to be checking people's submission times versus their requested exam time. So basically, like if you've got normal time, 12:40 p.m. you should be submitting to Gradescope. If you go over by like 5 minutes, we're not going to send you to the Honor Council. But if you take the quiz at 10:20 a.m. and submit the Gradescope at midnight, you're going to the Honor Council. I think Gradescope will tell you if it compiles, but Gradescope will tell you if it compiles, but it won't give you feedback on how many of our hidden test cases you passed. But if it doesn't compile, I would rather get the problem as done as I can get it. If there's one little typo that a person can comprehend and we can give you the points, we're going to do that. So don't don't kill yourself trying to get it to compile. I'd rather have it mostly done and the code is all there, but almost compiles, rather than have it a quarter done and get stuck on a compiler error and not proceed. So newbie 6799, yes, in fact it can be. If you really know your STL stuff, you can do the last one using nth element, and it's actually much faster than is required. It's faster than the solutions we gave you. Okay, so that's it for today's lecture. Sorry about the buffering and dead power supplies and stuff like that. I'm going to go get the exam finished and posted and eat lunch with my wife, who's been very impatiently waiting for us here.